looks good. And look, it's even recording that. Oh, lovely. All right. So let's go here. See if it's actually going to work. All right. I don't know if it's recording or not, but we'll find out the hard way. All right. So for today, you guys read a lot of Chapter 1, and I hope that you realized what I feel like is sort of the moral of the story of Chapter 1 is that we're going to really start at the beginning. We're not going to take for granted, I think, that you know a whole lot more than you already know. So, I mean, you're in good shape. What did you guys think about reading the textbook? Amy, what did you think of the textbook? Did you have a chance to get one? Did you have a chance to get it? Or you still?
Yeah, I got it.
Okay.
I haven't cracked it yet.
Okay, that's fine. Getting it is really like 90%. But do read it. All right, but anyway, so let me call out somebody who, raise your hand. So, all right. Yes. Yeah. Okay. Phil, did you raise your hand? Did you have a chance to look at the book?
Yeah.
What did you think of it?
It wasn't too bad. It wasn't hard to read.
Right, and it's not, and that's, I hope the way that you feel the whole way is that the psychologically will probably not be a very like violent semester. I don't think it's actually, this book is gonna sort of help us through. As long as you read it beforehand, it's gonna really help you feel more confident in class. All right. Okay, so let's go ahead then and begin. I know I can't see half you guys when I stand over here, but this is just my arrangement, I guess. But I do want to cover the material in the book. Again, not everybody has it. You know, some people might have ordered it online, be waiting for it. So let's go through it. All right. So we are going to, that was written really messy, but space over here. All right. All right. So we began in Chapter 1. It's a really nice introduction. And I don't need this light on right here. That's not easy to see. Hold on just a second. Let me see if I can get the lights to turn off. Can you guys see okay? Do I need to turn off this set of lights here? Would that help? Might help. Darcy, could you see if you can get the last set of lights to turn off?
Can you also move the cursor off the screen?
I can move the cursor. This one here. All right, thanks. All right, so is that enough?
Yeah.
Okay. All right, okay. All right, so I think one of the interesting things that maybe you didn't know before was that there are actually 3 formulations of mechanics that can do all the same things, but that are completely unique. And so we have our Newtonian mechanics, our Lagrangian mechanics, and our Hamiltonian mechanics. We will get through Newtonian and Lagrangian this semester. And at least you'll be introduced to Lagrangian. We'll use a little bit more next semester and do Hamiltonian next semester. So there are 3 formulations of mechanics. We've got Newtonian, Lagrangian, and Hamiltonian. Those are just fun to say, right? I feel smarter already. Okay, and all of these can describe all classical motions and phenomena. So we need to remind ourselves that this is classical mechanics, which means that we will only operate in a certain domain. So that if we have size on this horizontal axis and speed on the vertical, you guys who are in 240, 250 with me have seen this plot before. We have this realm here where things aren't going fast compared to the speed of light, and things are big compared to molecules and small compared to solar systems. And in that realm where things are of that size and speed, we can apply what we will learn in this course, classical mechanics. Okay. However, if things begin to move faster than that, and close to the speed of light, then we have to involve special relativity effects. If things are larger than the solar system, then we have to start to include general relativity effects. Actually, they become non-negligible for macroscopic purposes. All right. They still exist, but they're teeny. All right. And then also, if things become small on the order of a molecule or so, then we have to include quantum mechanics, and classical mechanics will no longer apply. But in this region, classical mechanics will apply. All right. And that's a large region. All right. So let's move on. So the next thing that the book introduces is describing locations in space. So I think that we've already, again, I don't want to assume that you know anything, but in order to describe location of anything, we're going to use, a Cartesian plane, like Descartes made, and we're going to have to place that into a frame of reference. So in order to describe a location of a point P, we will need a frame of reference, and within that frame of reference, we will place a coordinate system. All right. And again, later in this chapter, we'll learn to use inertial frames of reference, which are defined by Newton's first law, so that all three of Newton's laws can hold, and we have the simplest formulation of Newtonian mechanics. All right. So in order to describe the location of something, we introduce the location vector. All right, so the location of the point P can be represented by a vector. So I can represent it like so. All right, and what this has is it has three components. So we're going to imagine that I have a rectangular coordinate system. And usually when you draw, your book also does the same thing. You'll see beginning on page 22 that you see a lot of three-dimensional drawings. And when you draw a three-dimensional coordinate system, you make X, it's supposed to look like X is coming out of the page at you, and Y and Z are lying in the page. So you're supposed to have a 3D effect like that. All right. And so, like, let's say our point P was here. There would be the vector R here, and it would have a Z component, like so. If I can draw this a little higher. There's its Z component. And it would also have an X component and a Y component here. I hope that you guys can see what those are. This is the Z here. Okay. All right. So we can represent that. In this case, I've chosen what are called rectangular coordinates, which is what we're going to be beginning with. All right. So in this case, I say that in order to get to point P, I have to move a distance x in the x direction, and a distance y in the y direction, and a distance z in the z direction. And notice that our unit vectors here that represent the phrase in the x direction, in the y direction, in the z direction are x, y, and z hat. So they're not I, j, and k hat, although a lot of books will use I, j, and k hat, and even other things. Your author wisely chooses to use this, which is a very common and convenient choice. All right. Also, so in this case, we can represent it as a sum, this vector R here, as a sum of a vector that goes in the y direction, a vector that goes in the x direction, I'm sorry, a vector that goes in the y direction, and a vector that goes in the z direction. And the sum of those three, which is called the resultant, that extends from the tail of the first to the head of the last, is obviously our vector R. So that's why we can write it as a sum. All right. We can also express that position just in terms of components, x, y, z, this would be fine as well, and that will also be used by your author. All right, another thing that your author will use is R1, R2, and R3. So we can also write this as R1 in the x direction plus R2, meaning the second component of R, in the y direction plus R3 in the z direction. Although we can make that even simpler, because instead of x hat, y hat, and z hat, we'll call this unit vector 1, unit vector 2, and unit vector 3. So let's do that. So we'll have component 1 along unit vector 1 plus component 2 along unit vector 2 plus component 3 along unit vector 3. And you might say, why aren't we using u for unit vector? Well, we kind of are, it's just we're speaking German. So that E stands for eins, which is 1, so it has a length of 1. Okay. All right, and we can shorten this to a sum of n, or I guess your book uses I, equals 1 to 3, r sub I, e sub I. All right, so those are all very elegant ways to represent a vector. I see 1, 2, 3 that you will want to become very familiar and comfortable with. But they can all three be used interchangeably for the same information. All right. Okay. Come in. I don't know. Did I start early? It's 1:15.
Starts at 1 and goes to 1:50.
Oh, sorry. Okay.
Somebody sure.
All right. Okay. So next thing we need to talk about, so we just so far have only talked about location here, and the ways that we're going to represent location is bring you up to speed. So location of the point P, we're going to express it as an R with an arrow on top of it. In rectangular coordinates, we can express it as a sum, or we can express it in terms of components, or we can express it with a summation formulation. That's it. All right? Okay, so I'm going to go ahead and move on. Next, we need to talk about vector operations. All right, so we have several that we need to discuss. And again, I apologize if you have no rust on you whatsoever, but I'm going to be complete just to cover everybody, just in case you're rusty. We have addition of vectors. Okay, and so addition of vectors is we write the vectors as though they are adding, all right? And whenever you do add vectors, what you get is either called a sum or a resultant. All right, and what we're actually thinking of is, let's say that we have two vectors. A lot of times when you want to add vectors, you arrange them tail to head. So let's say the vector R is maybe here. And the vector S is maybe here, like so. In which case the resultant, I've arranged my two vectors, which can be moved around in space. I've just arranged them so that the tail of the second is at the head of the first. And if there were more, you would just continue to arrange them. And the resultant vector extends from the tail of the first to the head of the last. Okay? All right. And so you will see that in order to get the x component of the resultant, I had to take the x component of the first and add it to the x component of the second. You see that? So this is Rx, and this is S sub x. All right, so in order to get the x component of the resultant, I'll have to add those two. And the same will be true for the other components. So that the resultant vector in component form, I can write it as R, and this is sort of a combination, again, trying to use this notation here where sometimes the x components are called R1s instead of R sub x, which would be fine. And I think your book is doing a good job trying to mix it up so you get used to all the different ways that you can see vectors. R1 plus S1 is my first component. R2 plus S2 is my second component. R3 plus S3 is my third component. So hopefully we all understand what that means. Are there any questions at this time? Cool. All right. So there are, in terms of a physics application of this, when two or more forces act on a single point particle, the effect, resulting acceleration, is as though there were a single force acting that was the vector sum of the two. So that'd be the sort of places where we have to use that. Okay, so let's move on. Multiplication by a scalar. All right. I'm going to move this page here, but I will get around to it. Are you guys going to want me to scan and put these PDFs on the website, or are you okay without them? Yeah? Yeah, okay, I can do that. Okay, but nothing will be as good as your own notes, so please continue to do that. Okay, so multiplication of a scalar, multiplication of a vector by a scalar is basically, the following. So if I have a vector, again, this is always, if it's just 2D, just think that these are always x, y's. So if I have a vector r, and I want to know what is the vector 2r, it is the vector that is directed in the same direction as r, but having twice the magnitude. All right. So in that case, what I am doing is I'm taking a number, just a constant, and multiplying it by a vector, which in this case is r. And as a result, my three components are going to be CR1, CR2, and CR3. Or my x component of the resulting vector would be c times x, c times y, c times z, if you want to think about it in terms of letter components. Okay. Again, the physics application of this that comes up a lot is when you think of this constant as being the mass of a particle, and this r as being a vector that would be the acceleration of the particle. Obviously, that's going to show up in Newton's second law and be very important. All right, so that's how that is done. So let's move on. The scalar product. The scalar product of two vectors is also known as the dot product. Okay. And in this case, in order to find the scalar product of these two, it would be the product of the first two components, so that would be R1, S1, added to product of the second components, R2, S2, added to the third. All right? Okay. We will also, this is where you can start to see where it becomes, kind of convenient to use these subscripts, because I could rewrite this sum as a sum from 1 to 3, and in this case we're going to use n, of r sub n, s sub n. Okay? All right, so that would be the type of reason that we would use this type of format, is that it lends itself nicely to that type of analysis through summations. All right, but also, if you have two vectors and you're calculating their dot product, let me go ahead and draw them here. When you're calculating a dot product, it is useful not to arrange them tail to head, as you did when you were doing the addition, but to arrange them tail to tail. Because the dot product is also equal to the magnitude of the first, which we will call r, the magnitude of the second, which we'll call s, times the cosine of the angle between them, which we'll call theta. All right? Okay. And dot products are useful for, as an example, for the increment of work. So that's kind of a loaded word. Let me go ahead and write it out. As a physics example, the increment of work, meaning an infinitesimal amount of work that was done by a force acting on an object through an infinitesimal distance, can be written as that applied force dotted with the infinitesimal distance that the object moved. All right. And so there's an example of dot product in physics that we will need to be able to apply dot product. Okay. And another application of dot product that is important is finding the magnitude of vector itself. So let's talk about magnitude of a vector. I've already included it here, so back it up just a moment. When I want to represent the magnitude of the vector, I will just write the vector without the arrow. And that will... You can also write that like so, with the absolute value sign. Okay, but it will be quicker just to write it this way. And that will be equal to the dot product of a vector with itself quantity square rooted. All right. And we can see that that will always be equal to, just applying this first expression here, r1 squared plus r2 squared plus r3 squared. Just plugging in for this dot product from the expression above. That should make sense to us anyway from the Pythagorean theorem, because if we have a vector r, here's the x component, the y component, and the z component. Here's my vector r. Here's its z component. Let's see if I can. So I'll go ahead and, just for this vector, if you don't mind, I'll go ahead and just use z to represent its z component. It also has an x component and a y component. Hopefully you can see those on the figure. Let me trace them in red for you. So I've got this x component here, the y component here, and the z component here, right? Okay. So if I ever wanted to find the magnitude of r, I could just use a Pythagorean theorem saying, okay, well this is, these axes are defined as perpendicular. So in a Cartesian plane, that is the case. So I know that I have a right angle, for instance, here. So let's call this length here, let's call that r sub xy. And I know that r sub xy squared plus z squared will be equal to r squared. All right, from the Pythagorean theorem, are you guys okay with that? And r sub xy, similarly, is the hypotenuse of another right triangle, right there. So that r sub xy squared is equal to x squared plus y squared. So that in the end, I have both of these yielding that r squared is equal to rxy squared, which I can plug in x squared plus y squared. Quantity plus z squared. All right. So that's great. And that is also in agreement with our definition of the scalar product. So that's fine. So we can also know that this must be the case also by applying this expression for the dot product, where we would get magnitude of r times the cosine of 0, because the vector is always parallel to itself, which would give us magnitude of r squared. Okay. Is everything sort of hanging together for you? All right, cool. All right. The vector product, which is also known as the cross product. All right. So in this case, did I move that away too quick? Bring that. All right. So in this case, I'm going to note that whenever I take the cross product of two vectors, the product itself is another vector, whereas in the scalar product, the product itself was a scalar. All right. So in this case, if I have r cross s, and I want to know what the product is. I'll go ahead and give it a name, give it a symbol. In order to find that cross product of R and S, I have to take the determinant of the following 3x3 matrix. Its top row is x hat, y hat, z hat. Its second row are the components of the first vector. So we'll go r sub x, r sub y, r sub z. And the third row is the components of the second vector. So s sub x, s sub y, s sub z. All right. And since, again, I'm not going to rely on memory by any of you, I'm going to show you how to take that determinant. So in order to take the determinant of this 3x3, I take the top left element, x hat, and I multiply it by the determinant of what's left of the matrix after I take out that element's row and column. So then I'm left with this 2x2 right here. And its determinant is always the product of these two minus the product of those two. All right? So that's going to give me x hat times ry sz minus rz sy. Now, I repeat the process except with a minus sign with the next element over. So I get minus y hat. And now I have to take out its row and column and take the 2x2 determinant of what's left, and I'll get rx sz minus rz sx. Right? Then I go to the next element, and again I have to switch the sign that I'm putting in front. So that takes me back to a plus sign and a z hat. And the 2x2 determinant of what's left when I take out the row and column that z hat is in, and what I get is rx sy minus ry sx. Okay? And that's how you take the 3x3 determinant. And this comes up, let me see if I can try to illustrate this. Let me draw a figure here. So let's say that I have two vectors. They're both going to be lying in the xy plane. Okay, so this one's r, and this one's s, and both of those are lying in the xy plane. Now, when I do this cross product, you'll see that all my z components are 0, and as a result, everything here is multiplied by a z component, except for the two terms that are multiplying the z hat direction. So I know that from this, that whenever I have two vectors, the cross product will always be in a direction that's perpendicular to the plane that's defined by those two vectors, that contains those two vectors. All right, and in terms of which direction, we'll talk about that in just a minute. So this is one way to write the cross product of these two vectors in terms of their components. We could have also written it in terms of their magnitudes. It would be the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them in a direction that comes from the right-hand rule. All right, and so the right-hand rule is this. If you start with your right hand, you can point your fingers in the direction of the first vector, which is sort of supposed to be out of the page, and into the second vector, and your thumb will point in the direction of their cross product. Now, you knew the cross product was going to be perpendicular to the plane that contained them anyway. The problem is that when you do that, it only limits it to two directions, and then doing the right-hand rule tells you which of those two it is. A lot of people also do it this way, like this. This represents the direction of the first vector. This represents the direction of the second vector. This represents the direction of the product. So I have to turn it until it's pointing the way I want, and I get the same result. You guys okay with all that? All right, good. All right. And I think that we know that, a time when this comes up is rotation. So, for example, let's say that you have a force. Maybe it's over here, maybe it's acting straight upward in my figure. Oh, drawing's not good. X, Y, Z, and then over here I've got a force acting. And maybe it's acting on an extended object, like that. Okay. So what this force is going to do is it's going to tend to torque this object. And so in order to get an expression for that torque, I would draw for instance, the torque about my axis, about my origin of my axes, I would draw an R vector to where that force acts, and the cross product of the R vector and the force would be equal to the torque. Now, your book uses a capital gamma for torque, and we'll deal with that more when we get there. Okay? All right. So clearly in this case, with the force acting up and R also being in the YZ plane, the torque is tending to cause a rotation about the x direction. And that's what the direction of the torque means, is it describes the direction about which the rotation is occurring, the direction of the axis about which the rotation occurs, or tends to occur. Okay, so are there any questions about the dot product or the cross product? Nice. Let's move on to differentiation. All right, so, and specifically of vectors. Okay, and again, I think your author does a nice job of telling you not to panic if you haven't had a, vector differentials course, because this book and this class is going to provide you with everything there is to know about vector differentials. So let's go ahead and start with the simplest case, which is the time derivative of one-dimensional vector, so something with just one component. So we'll do the, how am I doing this? Okay. The time derivative in 1D. All right. So for this, we're going to allow x just to represent the x component of some maybe location vector. And it's going to depend on t, all right? So in this case, it'll be a function of time, all right? Have a dependence on time. Okay, in that case, we're going to define dx of t with respect to time. Now this is a little bit confusing because these two t's represent two different things. This is, I'm taking the derivative of x at the value t with respect to the variable t. All right? Okay. All right. So, my gosh, I am cramped in here. All right. All right, so in order to do that, we're going to define this as the limit where delta t goes to 0 of, do I want to use delta? Sure, we can use delta x over delta t evaluated at that value t, which is the thing that's in here. Okay? You guys all right with that? Okay. So another way to write that is that it is equal to the limit where delta t goes to 0. This delta t going to 0 is what this, taking care of this denominator t variable. All right. And it also is this delta t here. In that limit, that delta t becomes very small, and we call it dt, which is infinitesimal. All right. So let's remember our definition of derivative. So it is the value of x at the time t plus delta t minus the value of x at the time t divided by the time elapsed, which would be t plus delta t minus t, also known as delta t. Okay. All right, so that's how we do time derivatives for one dimension. Let's move on to 3. Okay. Time derivative in 3 dimensions. Okay, so again, we're going to have to define the operation. So we have dr dt. By the way, I'm going to put a colon So this R is my location vector that now has 3 components, not 1. And this will be defined as the limit where delta t goes to 0, delta R over delta t evaluated at t. And we can again write that. Goes to 0 of R when time is equal to t plus delta t minus R when time is equal to t divided by the time elapsed, which is t plus delta t minus t, also known as delta t. Okay. So those are our defining equations. Now, we can also write this plugging in for, I'm going to go ahead and go a little bit fast and loose right now and say I'm going to plug in, I'm going to know what the difference between these two vectors is. So wherever I see this, I'm going to say that's going to be delta x in the x direction, and delta y in the y direction, and delta z in the z direction. And I'm going to be dividing that by delta t. Okay. Well, if I look at this, then I would say, okay, I'm going to divide each by delta t. All right, which is going to give me this limit where delta x over delta t, and the limit that delta t goes to 0, I had just defined that previously as dx dt. So I'm going to write this now as dx dt in the x direction, plus dy dt in the y direction, plus dz dt in the z direction. Now, I have gone from this line here that holds absolutely to this line here that step I'm going to give a star. Okay, and I'll come back to the star because there are some subtleties and approximations that I've made in that line. All right, but let's for the moment put a pin in that and continue to move on. So now let's say that we want to define the velocity as a function of time as the time rate of change of location as a function of time. All right, that should be an R. I apologize. All right. Then what we have is I can write, well, obviously, if velocity is equal to that, I can write it in terms of these 3 terms. Just substituting for dr dt. And I also know that anytime I have a vector, it's going to be able to be rewritten as its x component in the x direction and its y component in the y direction and so forth. So I can write this as v sub x in the x direction, plus v sub y in the y direction, plus v sub z in the z direction. And I see that what I get here is that I've made all these definitions such that, the symbol here means such that. I'm going to be using a few symbols in this class. All right. The result of this is that the x component of the velocity of a particle is equal to the derivative of its location, the x component of its location. And the y component of velocity of a particle will be equal to the time derivative of the y component of its location. And the z component of the velocity of a particle will be equal to the time derivative of the z component of its location. Okay. All that hangs together pretty nice. But why is that so? There are subtleties, and the subtleties are right there. So let's address them. Here are the subtleties. That we had to use at the start. Okay, first of all, we have assumed that all the vectors involved were differentiable. And that is true. For physical quantities and things that actually occur in nature, they do change continuously. In classical mechanics, all right? Now when you go to quantum mechanics, you'll have something disappear here and show up over there. Then classical mechanics can be broken. We're going to have to make a whole new thing, and thank heavens Hilbert and Dirac took care of that. That's for a different year, okay? All right, but we're going to say that everything that we see, if you were located here and you went there, then you went there through some continuous line. You didn't disappear and then show up somewhere else discontinuously, all right? So, and that will be true of all natural quantities. So this step, your math professor might not allow it, but in physics, we're going to allow it because it relates to a physical quantity. All right? Are you okay with that, Ryan? Yeah, right? Okay. All right, so let's go ahead, though, and point out what we have done. So all the vectors we encounter in nature are differentiable. That means that they'll change continuously, and these can be defined. But that is an assumption that we are making. Change continuously. And by continuously, I don't mean all the time. I mean that they vary and they can't be discontinuous. And are therefore differentiable. Therefore, it's going to be 3 dots like that. All right, what's another subtlety that was involved there? Well, another thing that I used there was actually the product rule, although I didn't discuss that I used the product rule, but I should do. So we need to remind ourselves that vector derivatives have the same rules. They will wind up having the same rules as simple derivatives. So for instance, we've got the sum rule, d dt of r plus s is going to be equal to dr dt plus ds dt. That is called the sum rule, and it indeed does hold. All right. We will also have d dt of, let's say, f times r. And so we are going to have the product rule also holding. So this will be df dt times r plus f times dr dt. And that's called the product rule. For multiplying a vector by a scalar. Okay. So in this case that I have the product rule, if I consider the vector x, which is purely in the x direction. It has a value of x directed in the x direction, a magnitude of x directed in the x direction. Then, if I want to write dx dt, what I will get is, again, I have to apply the product rule. So I'll get dx dt times x hat plus x times dx hat dt. And I will make the assumption that once I choose a coordinate system, I stick with it and it remains constant, and therefore my x hat, y hat, and z hat will never have any time dependence. So in that case, this term here will be 0 because dx hat dt will be 0, and I'm left with just the first term. Okay, so again, the subtlety that I have made in this step is that I have decided that my coordinate system is going to stay fixed in time. Am I okay in time? All right? Okay. So those are the subtleties from that line to the next. The next thing I want to talk about is time, although am I out of time? I've got 1 minute. What was that?
Okay.
Oh, okay. It's like, are they like putting passing period bells in the college now? Freaking me out. All right. So the next thing we need to talk about is time. And I'm obviously going to learn how to talk faster before next time. All right. So we probably maybe heard at some point in our lives that according to special relativity, the value of a time variable can depend on constant relative velocity, Remember the guy in the train car, and he turned on the light that was in the middle of the train, and the light waves went out and it hit the both ends at the same time, whereas this other person was viewing it from the side and said, oh, that train car was moving fast. Therefore, the back wall came up, and the light hit the back wall before it had a chance to hit the front wall, and so those things were not actually simultaneous. Well, if I define a time t as a time when both of those waves hit, it's not even defined for this other person. So again, we are going to allow simultaneity to exist, meaning that things can occur as a function of time and that there's only one time variable to think about. And we're going to assume that that time is agreed upon, even for frames of reference that are moving at constant velocities to each other. And that will be a very good approximation until you start going close to the speed of light. So we're good with that, all right? We're going to be good with that. All right, so basically we're considering the classical limit, which means gamma is 1, or the Lorentz factor is 1. All right, so we move on next time, and my plan is to finish the chapter, but I'm going to have to talk faster. All right, see you guys on Friday, and I'll make the first homework assignment on Friday as well.